Alright guys, so our next section is 2.4, complex numbers. So if you guys think back to, probably Alg 1's first time you really introduced the whole concept of, square roots, and that there was some kind of an issue where we couldn't take the square root of a negative number. Okay, you guys now at this point should have seen this several times, at least in Alg 2, and a little bit more in pre-calc. All right. Remember, complex numbers or imaginary numbers are going to come from situations where I'm trying to take a square root of something, and in fact, there are no two real numbers that give me that result. Like whereas square root of 16, 4 times 4 would give me 16, so therefore square root of 16 is 4. But if I throw the negative in there, there is no number that when I square it, or at least no real number that when I square it gives me negative 16. Because either a negative times a negative or a positive times a positive guarantees I'm getting a positive result. So the problem that we run into is that negative. All right, so complex numbers are exactly how we are going to address that. So let's first introduce the imaginary unit. So the imaginary unit I comes from the square root of -1. And if I have I equals square root of -1, if I square both sides, I also get that I squared equals -1. Okay, think about it, that doesn't make sense. I'm taking some number, some value, and I'm squaring it. When I square some number or some value, I should get a positive, right? But because it's the imaginary unit, and by definition of the imaginary unit, I get that negative number. So let me come back to my example from just a few seconds ago, square root of -16. So the way I'm going to break this down, at least in the most elementary way, you guys don't have to necessarily do it with all these steps, but I'm going to break it down into square root of -1 times square root of 16. Okay, or I could actually really write them in the other order because of the way we're going to write this in the next step. But the square root of 16 is then going to give me a 4. And by definition of the imaginary unit I being the square root of -1, the square root of -1 is going to give me an I here. So the square root of -16 is going to give me 4i. Right? So a couple other things here. Imaginary form or imaginary numbers are a complex number. Complex numbers are of the form a plus bi, where the coefficients a and b are real numbers, and then the bi is the imaginary component. So an imaginary number specifically is where we have a complex number a plus bi, where b cannot equal 0. All right, I must have that imaginary component. Okay. Now the one thing that's kind of interesting is that complex numbers are of the form a plus bi, where a and b are real numbers. So if you think about that, 0 is a real number. So that means that our b value, or our imaginary component of that complex number, can actually be 0, which would leave me simply with a real number. Okay, so what that implies then is that when we have our number sets, you have the whole or the natural numbers, then you have the whole numbers, integers, which is z, then you have your rational numbers, okay, then you end up with the real numbers. I'm kind of running out of room here. So we have our real numbers, but our real numbers are actually a subset of the complex numbers. So all of our real numbers are actually a complex number. Just a complex number specifically where the imaginary component happens to be 0. Okay, so I've just expanded our number sets. All right, and I'll see for class, I'll get a better graphic than the one I scribbled here, but it'll still show the same thing. Okay, so operations on imaginary numbers. I can add, subtract, multiply, and divide imaginary numbers very much like we deal with real numbers and also algebraic terms. Okay, so when I am adding or subtracting imaginary numbers, I want you to think like terms. Okay, whereas if you had 2x plus 1 plus 3x minus 5, I can combine the x components and get a 5x, and then I can combine my real components here and get a -4. Well, I'm going to do pretty much the exact same thing, except now I'm going to just deal with the imaginary numbers. Okay, So when I take a look at this, my real components, I'm going to have 3 plus 2, or 5. And I have 5i plus negative 2i, or positive 3i. Okay, if you were subtracting imaginary numbers, one thing to keep in mind, let's say I have 2 minus 3i minus the imaginary number, I don't know, let's do 5 plus 6i. I need to distribute this negative to both terms. Here I have 2 minus 3i because I'm subtracting the entire imaginary number here. Okay, and then now I can combine like terms, so I would have negative 3 minus 9i. Okay, so just one or two things to kind of keep in mind there. Don't forget if you're subtracting to distribute that negative. In terms of multiplying imaginary numbers, okay, you're going to possibly FOIL if you have two complete complex numbers like we do here. And you're going to follow the same exponent rules you would for variables. So if I had x times x, I have x to the first times x to the first, I add those exponents, I get x squared. If I had x cubed times x squared, I add those exponents because I'm multiplying like bases, and I would get x to the fifth. The same thing is going to happen here. If I have I times I, I'm going to get I squared. And if I had I cubed times I squared, I'm going to get I to the fifth for the exact same reasons. Okay, so let me go through and let's work this problem out. So I'm going to use FOIL or distribute. So I'm going to distribute the 2 to both numbers in my second set of parentheses. So we're going to 8 minus 4i. And when I distribute the 3i, I get plus 12i minus 6i squared. But now I want to go back to one of my original slides where I defined the imaginary unit. Remember I said I squared equals negative 1. So when we're dealing with, square roots, I always have to simplify. I have to take any perfect square factors out of that radical. When I have fractions, I always have to have things completely reduced. Well, we actually have the same thing that happens with imaginary numbers. I'm not allowed to leave any power of I greater than 1. So right now, this negative 6i squared is a problem because I have a power of I that's greater than 1. But I know this equivalency where I squared equals negative 1. Okay, so what I can do is make a substitution here. So I'm going to have 8 plus, when I combine like terms, 8i minus 6 times negative 1. So I really have negative 6 times negative 1, or positive 6. So when I combine with my other real number here, I end up with 14 plus 8i. Okay, so please don't forget that when we're performing these operations, we do have to account for and simplify any powers of I greater than 1. Okay, so I guess you're probably maybe thinking, what do we do if that power of I is something larger than squared? All right, so we have a couple powers of I here. The first one, anything to the 0 power always equals 1. All right, it's one of our algebraic definitions, and it holds true here. I to the first is simply I squared, I already said, was negative 1. So let me come over here to the side. I squared is negative 1. But if I had I cubed, you would agree, can be written as I squared times I to the first. Well, if I squared equals negative 1, don't I have negative 1 times I, or negative I? And if I had I to the fourth, couldn't I rewrite that as I squared? Well, I squared is negative 1, but negative 1 squared is positive 1. And if I had I to the fifth, just for example, this could be written as I to the fourth times I to the first. Well, I to the fourth is 1, and I is I, so I to the fifth equals simply I. Okay, so the one thing you're going to notice is that these repeat. Right? If I have I to the sixth, it's going to be negative 1. If I have I to the seventh, I'm going to have negative I. I to the eighth is going to be positive 1. Okay? So what we can do is look at remainders, divisors and remainders. Okay? So if I have a larger power of I, so let's just, for example, let's say I to the fifth. I showed that one here. But if I had I to the fifth, right? If you think about quotients and remainders, if I divide 5 by 4, 4 goes into 5 one time with a remainder of 1. If I had I, let's do to the 14th. 4 goes into 14 3 times with a remainder of 2, right? The remainder of 2, I have I squared equals -1, and I'm using then, once I've done the remainder portion, I'm using these powers up here to simplify that and come down to our final answer, right? Essentially what we're doing is each of the multiples, and let me show you I to the 14th here. I to the 14th, I could write this as I to the 12th times I squared. And I to the 12th is simply I to the 4th to the 3rd power, and then times that I squared. Well, I to the 4th is 1. 1 to any power is always 1. So here I get 1 times I squared, and the I squared we already said was -1. Okay, so you can do it the long way, where you break it out using your exponent rules and everything else and simplify it like that. But if you remember the quotient remainder, that the remainder is what's left over, essentially everything else is a power of I to the 4th, which just becomes a 1, right? So all you need is that remainder portion, and if you remember these 4, I to the 0 is 1, I to the 1st is I squared is -1, and I cubed is -I. Okay, then you can simplify any larger power of I. You can also do that in your graphing calculator. So if you have a really large power for some reason on I, under your math menu, there should somewhere in there, and I'd have to look to see exactly where, but there is a remainder function in there. We can take a look at that in class tomorrow. Complex conjugate. So if I have a complex number, and usually with complex numbers you use the variable z, but not always. And just because you see a variable z being used, it does not imply a complex number. But when we're talking about complex numbers, it's common. Okay, so z equals a plus bi. All right, for some values a and b, then its conjugate is a minus bi, and that's usually written z with a little bar over the top. Okay, so there's a reason that we have the conjugates, and that we would possibly use conjugates, and let me show you. If I have a plus bi times the conjugate a minus bi. Again, for any numbers a and b, it doesn't matter what they are as long as they're real numbers here. So if I FOIL this out, I'm going to end up with a squared minus abi plus abi minus b squared I squared. Notice that negative abi plus abi are opposites, right? They're like terms and they're opposite, so they cancel one another out. So I'm left with a squared minus b squared times -1, because I squared was -1. So what I get here is a squared plus b squared. And the other thing I just actually demonstrated to you here is that, remember, we had our difference of squares formula, where if you had a squared minus b squared, it factored when we're talking about quadratics to a plus b times a minus b. All right, and we said it only worked for differences of squares. It had to be subtraction. Well, I just demonstrated that a squared plus b squared will in fact factor to a plus bi times a minus bi. Okay, so this is our sum of squares formula. And our sum of squares, if we're dealing with real numbers a and b, is also going to guarantee that we get imaginary values or imaginary factors. And it's also going to guarantee that we're going to get imaginary solutions when we get to that point as well. Okay, so for right now, I wanted to show why the conjugates are important, that they cancel out all of the imaginary terms. So when I multiplied these together and simplified, I was left with something that only has real terms, which is really important for me. Okay, we're going to deal with the factoring and solving part here in a little bit tomorrow. But right now, I want to be able to get rid of or clear an imaginary component. And the main reason that would be is if I have an imaginary component in my denominator. Okay, just like when we dealt with radicals, I was not allowed to leave a radical in a denominator. I can't leave a imaginary value in my denominator either. If I simply have just the bi portion, there's no a plus or minus the bi. Then I just multiply by I over I and I cancel it out. And it's really simple. Okay. But if I have a complete imaginary or complex number, a plus or minus bi, I then need to multiply by the conjugate. So here, my denominator, I have 2 minus 7i. So 2 minus 7i is going to have a conjugate of 2 plus 7i. So I want to multiply by 2 plus 7i over 2 plus 7i. So in my numerator, I'm going to distribute. I'm going to get 10 plus 35i. And in my denominator, I'm going to FOIL, and I'm going to get 4 plus 14i minus 14i, and minus 49i squared. The 14i and negative 14i cancel out. All right. Negative 49i squared. I squared is negative 1, so really here I have plus 49. So I'm going to end up with 10 plus 35 35i, pardon me, divided by 4 plus 49, or 53. I need to look and make sure that between my three coefficients here, I don't have any common factors. In this case, I do not. If I do have common factors, we need to factor them out and reduce. But since we have no common factors here, we are done. Okay, the next thing that I want to talk about is interval notation. It doesn't necessarily have to go with complex numbers, but this is a good place to put it because we're going to start talking about solutions and intervals here in the next section. So I want to introduce it. Our book uses interval and also set notation on a regular basis. Okay, so we are up until now, we're very much accustomed to, for an infinite set, seeing, solutions such as x greater than or equal to 2. Okay, it's not that it's wrong to write it that way, but there are some reasons, and when you get into some more advanced math, interval notation becomes more convenient for a series of different reasons, and also in terms of how you represent different types of sets in other applications. So we're going to start introducing interval and also set notations here pretty soon, or here now. Okay, and we're going to start using them pretty soon. So if I had something like x greater than or equal to 2, this is going to be all the x values, if I think about it on a number line, from 2 with a filled in circle through infinity. Okay, so what I'm going to end up with is all the values starting at 2 and including 2 going through infinity. And when we use interval notation, our endpoints are either going to be brackets, right, for the left and the right endpoints, if we have the or equal to. And we're going to use parentheses for left and right endpoints if strictly greater than or less than. Okay, so here I'm looking at if I have, less than or equal to, greater than or equal to, parentheses when equal not included. Okay, and what I mean by equal not included is I don't have an equal sign, so the endpoint is not included. Okay, the other time we're always going to use parentheses is if we have infinity. The reason we're going to use parentheses with infinity is, well, whatever you can define as an infinity that I can include, I can say, well, add 1 to it, and I have a new infinity. Okay, so we can never actually reach infinity, so we can't include it. Therefore, we must use a parenthesis. Okay, so anytime you would have had a open circle, okay, open circle like that first one, negative or 1 through 2 with open circles on both ends is parentheses 1 through 2, and it's all the points between 1 and 2, not including those endpoints. If I have, and that's considered an open set. If I have a partially closed set or a partially open set, that means I have one endpoint that's closed, one endpoint that's open. So here I have everything from 1 to 2 with 1 being included. So I'm going to use the bracket to show that I'm including the left endpoint of 1 through the right endpoint non-inclusive of 2. Okay, and the one thing I was taught, and I don't remember exactly where, the brackets are used for the equals. And if you think of the top and the bottoms of those brackets, they kind of look like an equal sign. Okay, so you guys can go down through here and look at a lot of these other examples. The other thing that's going to be Important is you do write this in order of smallest on the left to largest endpoint on the right. Okay, these should always be in least to greatest or smallest to largest order. Okay, so when I'm dealing with something that's going to say negative infinity, I'm going to have negative infinity on the left, and then whatever the actual endpoint is on the right. Okay. So just again, another example or another graphic here showing what interval notation looks like with the actual inequality notation that you guys are used to, and also the graph that represents it, and then also a specific example of each type. Okay, when we're dealing with infinities, you only really have to write a negative when it's the negative infinity. You do not have to, and they do it here, you do not have to write a positive infinity. If you just write infinity without a plus sign, it's implied that it is positive. Okay, so take a look at this, start thinking about it, commit this to memory. I would write this somewhere that's accessible, right? And you can use either one of these two slides as an example, although the second one, like I said, because it has the interval, it has the inequality, it has the graph, I think this one is probably the one. If you're going to copy one down somewhere on a sheet of paper and put it somewhere convenient, this is probably the slide that you want to use to do so. Okay, that is all that we have for quadratics and for not for quadratics, for complex numbers and interval notation. We have quadratics coming up in our next lesson. So have a good night, and I will see you guys tomorrow.